Great. So, good morning, good afternoon, and good evening, depending on where you are in the world. Really happy and excited to being the moderator today for this webinar on fluid management, risk and uncertainty in early field development with Daniel and Veronica. I'll introduce both of them a little bit later, but first, just a few logistical items that's worth going through. So we have more than 100 registered participants, and we're using this system called WebEx event, which means that everyone is muted by default. But that doesn't mean that you can't interact. So if you have any questions, feel free to ask the questions in the Q&A chat box that you can find to the right. And just note that there is a Q&A box, and there is also a chat box. So if you want to ask Q&A, try to do that in the Q&A box, and the chat box can be more for if you want to talk to some of the panelists or talk to some of the other people in the meeting. The presentation typically are between 45 to 60 minutes, and then we have a Q&A session in the end. And the meeting is recorded, and that recording will be provided both on LinkedIn, YouTube, and also on Whitson Academy for those that are on or working for companies that are subscribing to Whitson Academy. For those who don't know what Whitson Academy is, it's one of our subscription products where you get access to both live virtual courses every single year, but you also get access to old on-demand pre-made courses that we've recorded that you can access on academy.whitson.com. So that's, for instance, items related to what we do here at Whitson primarily. So PVT, gas EOR, and gas condensate reservoirs are good examples of that. There's also courses related to petroleum engineering or more production engineering items, and there will also be courses on flow assurance related items here in the near future. Yeah. The next webinars after this is also on our webpage on whitson.com/training. So feel free to sign up to those next webinars already. They're typically related to things we do here at Whitson, and the next one coming up is with Christian from ADNOC, and he's going to talk about how to create a common equation of state model for one of the fields that he's been working on. And you can also sign up to our public courses on whitson.com/training, and that's also where you get access to and can find previous recorded webinars as well. So on that note, I'd like to introduce both of the speakers today, Daniel and Veronica. They're both with Repsol, and they'll talk about, as mentioned, fluid management and specifically risks associated with early field development. They've developed a lot of very interesting workflows, both related to QA and kind of QC work, so quality assurance and quality control type of work when it comes to fluids. And they've also developed a very interesting kind of traffic light system as well. So I'm really excited to have both of you here today. So on that note, I'll just go ahead and mute myself and then give the word or the screen to you, Danny. Let me just make you a presenter here. And now you should be able to share the screen. And there we go.
Can you see the screen?
Yep. Perfect.
Fantastic. Well, let's get started. Thanks a lot for the very kind introduction. We're very much fans of your work, spreading knowledge about PVT, flow assurance, and fluids in general, right? So this is our happy contribution to that effort. Today, Veronica and I are going to be talking about fluid management, risk and uncertainty, particularly in early field development. All right? And just to give you a bit more background on who we are, we work in the Repsol Technology Lab, which is the division inside of Repsol that is, let's say, developing new technology, new product solutions, let's say, to support our businesses, the existing ones and the ones that we are creating now that we have this pledge for net zero emissions. And in more particular, myself and Veronica were working in two areas of activity: production assurance related to fluids, material integrity, corrosion, flow assurance, presence of solids, and also flow analytics, going from very rigorous multi-phase models into also, let's say, more data science solutions in order to tackle the deliverability let's say, multi-phase samples. We not only do product development, we also do technology advisory to our assets. Based on our expertise, we're also following the developments of Repsol EMP, right? And that gives us a particular view because we enter into the projects very early, in exploratory phase, and we accompany them up to the production and the potential problems that they face there. So in terms of having a broad understanding of different kinds of fluids and also all the stages and how uncertainty is handled in each one of them, that's, as I said, that's our expertise, and that's part of what we want to share with you today. Yes, this also gives us the opportunity to spread our view or our vision on how we should handle fluids in oil and gas developments. First of all, having an integrated analysis. We have a team that know about all of the fluids, not only oil or gas, but also the water. We also tackle all of the phases at the same time, not only liquid and vapor, which is the standard, let's say, PVT, but also the solids. And also in the team, we have the laboratory capabilities and also the understanding of how to do the equations of state, the modeling of the thermodynamic behavior. So that gives us, as I said before, a comprehensive view and also an integrated relationship, because sometimes one aspect may influence another, maybe the geochemistry or the PVT is influencing the flow assurance and so on. So we're able to see that together inside of the same team. The second element I wanted to mention is the integrated equation of state. And Matthias mentioned it before as a unified equation of state. We are also trying to approach as whenever it's possible, the modeling of a system with an integrated equation of state that would be valid for all the different disciplines, not only reservoir, but production and facilities, working with the same equation to assure consistency. So these are sort of the two commitments that we try to apply in Repsol developments. Moving on, the focus of our conversation today is on fluid uncertainty, and it would come to no surprise that fluid uncertainty is everywhere during field development, from exploratory phase to development and production, and also that the range of uncertainty decreases with time, because at the beginning in exploration, you basically have no samples. You just have a prospect somewhere, and you have to work with a series of assumptions that have, let's say, high uncertainty. When you move into the development, you already have your first well, you start getting samples. You still have uncertainty because you may be limited in volume, the amount of experimentation you can do to actually quantify the behavior of that reservoir fluid. And finally, during production, we say it's low, but still there, because many times you're commingling reservoirs and you're not producing one single sand, and you cannot take that perfect sample that you would like to take because it's either impossible or it's too expensive. So you still have some uncertainty, but obviously it's decreasing with time. All right. So I'm going to start explaining how we work on that very early stage of the exploration phase when you have no samples available. Veronica will deal with the development phase, right? And if I start already talking about the exploration phase, in the end, we still have to take decisions in this phase. That's the bottom line. That's why we need to tackle that. That's why we need a workflow to address issues related to fluids, even at such early stages, because there will be questions asked about the fluid quality and what are the implications, even before taking the first sample in this exploratory phase. So trying to come up on why there is so much uncertainty, and I would say that it comes back to those, let's say, early textbooks where it looks like an oil reservoir is like a subterranean lake with just one single fluid, Of course, once you enter into the oil and gas industry, you realize there are different types of phases, dry gas, wet gas, condensate, volatile oil, black oil. You may have two phases in the same reservoir. You can have a gas cap, you can have a liquid leg. You may even find CO2 that has come from somewhere else mixed together with the oil and extracting some components and creating a cap that cannot really be called a gas cap because it's supercritical CO2. So in the end, the quality of the fluid that is in a particular reservoir depends on a number of processes, geochemical processes, either on the way from the source rock to the reservoir, or also inside of the reservoir, there are many in situ alterations, such as biodegradation, washing, cracking, even degrading based on gravitational forces. So in the end, I tend to use the analogy of a bottle of wine. Because if you have two reservoirs, they could be like two bottles of wine coming from the same owner, with the same grape, from the same year, but still maybe different in terms of the quality of the wine, because maybe one has the cork that has a small hole, so there's fluid compositional changes. No? And I'm saying all this because in the end we have to treat in this phase as if each reservoir was unique in terms of fluid quality, because in exploration phase you're going to be working with analogs, but you can never be sure that your fluid will be exactly that analog that you have selected, because there may be processes in that particular compartment that were not present in any other compartment in that basin or in that region. So how do we tackle uncertainty, and what's our workflow in these very, very early stages where we're being asked questions on fluid quality that we have to answer? No? And some of these questions are, how can we define the sampling strategy in the first well? Can we start assessing some of the feasibility scenarios? Can we start assessing, let's say, field architectures that will be used later on to assess the commercial value of one prospect versus another, and maybe prioritize what you're going to be drilling first? And finally, how can you do this in an unbiased way, trying to minimize the impact of, or let's say, the interests of a person, of a particular team inside of the organization? No? And in order to do so, we have developed this number of these workflows, no, that we have gathered inside of the what we call the Neptune tool, no, which in this exploratory phase are constituted by one database, one module that we call for fluid generation in order to assess fluid behavior, and another module that is in order to assess the impact in the operation, right? So what about the databases? What we have put, or what we're putting there, because of course this is a continuous effort, we have put information about fluids, no, for all the reservoirs in Repsol, in which there's a single fluid for the reservoir, no, as a reference fluid. No? And we have PVT data, we have flow assurance data, flow assurance in the sense of properties for solid formation. We have assay data to assess the commercialization value of that particular fluid. And we have a simple tool in order to select analogs, because imagine we are let's say, analyzing one prospect in the coast of West Africa, for example. So you would have an opportunity to look for fluids that are nearby, but not only that, but also look up for fluids that have maybe the geochemical processes, the geochemical alterations that you're expecting in that particular reservoir. A certain maturity, maybe you know that that area tends to have fluids that are biodegraded or not, et cetera, et cetera. So you're not selecting analogs only based on location, but also based on fluid properties. And we also have a tool to visualize properties. No, those selected analogs, you can see the trends in terms of API versus GUR versus saturation pressure, et cetera, so to have a trend and be able to apply it later on whenever you start having, as I said, this workflow in when you have no samples or when you start having samples. So what happens, just a couple of examples on what we have been seeing, right? Because, for example, on the left, we see a trend of fluid properties, asphaltane content. These heavy components tend to increase when you're decreasing the API. No, you may be having, as I said, you tend to have this trend of higher amount of asphaltanes for lower API, but sometimes you find samples as the one highlighted here that does not really follow the trend. You may think it's an error from the laboratory, but based on the, let's say, geochemistry knowledge, you may in the end conclude, as it was the case here, that this fluid does not follow the trend, but that's okay because there was a certain geochemical process of, let's say, gas coming into the reservoir and destabilizing the asphaltanes. So the sample that you get in the surface has no longer the amount of asphaltanes that it had originally in the reservoir because it has been deasphalted. Similar example on wax appearance temperature, that point over there seems to be out of trend. And again, you have to question, is that okay? Is that a problem in the lab? And again, for this particular example, it was a case where the geochemistry could explain why that heavy oil had a high wax appearance temperature. It was not a biodegraded oil, as typically you have with the heavy oils, but it was a, let's say, an immature oil that got to that particular reservoir. So a couple of, let's say, food for thoughts that sometimes there is a reason for a fluid to be an outlier, and having stored all this data together, not only for a particular basin, but let's say worldwide, allows you to identify outliers and start asking questions that sometimes are answered. Oh yeah, that was a problem in the lab. Sometimes they're like, no, this makes sense from a, let's say, a chemistry point. The next workflow involves, as I said before, when we're trying to predict fluid properties, in these early stages where you have no fluid sample, what we have come up is with a method in which you start with a very few properties, API and GUR with an interval, because you have to consider an interval in exploratory phase, right? And we have a method in which sequentially you calculate properties for PDT, saturation pressure, formation volume factor, for flow assurance, amount of solids, amount of asphaltanes, and so on, and also for the atmospheric liquid in terms of sulfur content, molecular weight, And with the help of Monte Carlo simulations, we're able to generate, let me go back again. We have sequentially correlations to calculate sequentially property by property, but we apply Monte Carlo correlations so that this is done under uncertainty, because we randomly pick one API, one GOR, you run the equation, you get the value, and by doing these iterations 10,000 times and so on, you end up getting a distribution, right? So we are able to actually determine, let's say, an average fluid property, a high quality or a low quality, trying to reflect with the fluids the same approach as you typically follow for the rocks in terms of P10, P50, P90, right? And in this way, in these early stages, we have an automated workflow to define what the fluid quality could be, right? In an automated way that I would say means that it's sort of an unbiased way. Where have we used this workflow to answer questions like the following? For example, what is the drawdown available for monophasic sampling? Imagine you have a reservoir as in the one in the top here, where you know where the gas oil contact is. You have a couple of samples there that in this case were contaminated samples, so you do have an uncertainty of what the saturation pressure could be, and then you have to extrapolate to lower depths for the next sample, and you want to make sure that you have the 200, 300 PSI available for drawdown so that that sample can be taken in a monophasic state, right? And in this way, select the adequate gauge for that sampling procedure. Another example is when you're getting already MDT data, so it's not as early as I was explaining before, but when you still have very tiny, let's say very few pieces of information, because with the MDT data you have GUR from the downhole fluid analysis, you may also have the pressure gradient, And we have used this methodology to calculate properties from another in order to predict a range of API that would be, let's say, coherent with available information and start feeding information to the commercialization guys so that they start having, as soon as possible, information of the value of the oil. Another example that we have applied in the past is for a basin where you have a lot of information of viscosity versus API. Of course, viscosity is increasing when API is decreasing. We had one particular prospect that was deeper and that was heavier and that had not been developed up to that point, but we had some information from MDT samples that were very contaminated. So there was some viscosity data that we didn't really trust. So we had to come with a value of viscosity in order to be able to run the visualization cases. And again, we applied the same methodology of using the available data with correlations and Monte Carlo simulations to predict the range of viscosity of that heavier sample. That again has limited information, but for that particular property, we did not believe the data that we were getting. Moving on, the last example that I wanted to share in this exploratory phase is when you are moving on and want to assess what could be the field architecture for that prospect, Because as I said before, we had a way to generate a P10, P50, P90 fluid in terms of quality based on those Monte Carlo simulations. And what we have here is just a way to translate. We have, of course, thermodynamic models, but also correlations to generate phase envelopes with the uncertainty, showing, as you see here with black, the phase envelope for liquid vapor. In blue is the hydrate. There are 3 lines, probably you cannot see it that well, but for the green line that represents the wax appearance temperature, there are also 3 lines there. So you have a phase envelope with uncertainty coming from the fluid that you have generated before. And then we have either the opportunity to import the fluid dynamic profiles coming from a standard simulator or commercial simulator, but we also have embedded a simplified tool based on historical relations of pressure drop, just to give you a hint of what would be the location of the wellhead in this pressure temperature diagram, what would be the location of the facilities, and in this way identify what could be, again with traffic lights, what could be the most risky elements of your production network. You can run several cases with pipe length, diameter, insulation degree, so you can start having some sensitivity of what would be required for that prospect to actually make a feasible, let's say, business case for development. But also that kind of approach where you represent pressure, temperature, phase diagrams with a trajectory of the fluid are very useful for sampling discussions, no? Because you can start discussing whether to go for separator or bottom hole samples. For example, here, we're estimating that due to the GOR expected, we're probably going to have either a gas cap or a saturated fluid. So you would not recommend bottom hole sampling for your PVT studies. You would go for separator sample. But at the same time, we're seeing that wellhead sample, sorry, that surface sample may be in the limit of having risks of wax formation. So again, you have to balance, do I worry by losing a little bit of waxes on the way to the surface? Is that okay? Should I go for what kind of bottles? If we've had asphaltene issues, not the case here, but you can also ask yourself, what kind of downhole bottles I need? Do I need pressure compensated if I'm expecting asphaltene issues, yes or no? So this gives you an opportunity to very quickly generate those field architectures and very quickly have an opportunity to show your colleagues what are the risks that you are identifying and how to justify a specific type of sampling, because in the end that's money. And by doing this, you are able to justify, for example, in this case, separator versus bottom hole for the liquid vapor sample. I'm reaching the end of my part. I just wanted to emphasize that in exploratory phase, sometimes we have to take decisions even before taking the first sample. So we need something, as we are doing now, to have a guided workflow to apply uncertainty, because in the end, each reservoir fluid is unique. You cannot assume that your analog is going to be perfect for your prospect, because again, reservoir fluids are like bottles of wine. And finally, these analogs may exist to help you predict fluid properties, but you have to select them with care, not only by location, but also if they have the kind of, let's say, geochemistry characteristics that you're expecting in this particular prospect. I'm gonna pass it to Veronica to continue with the presentation.
Thank you, Danny. I'm going to share my screen.
There we go. Then,
yes, I can do it, Matthias. Thank you. Do you see my screen?
Yeah.
Okay.
Excellent.
Okay. So, hello, everybody, first of all. Well, now we, as Daniel have mentioned before, we are going to move from exploratory phase, where we do not have any sample available, to development phase, where we have the first sampling campaign. No? In this phase, when samples are available, the uncertainty is reduced, but we still have some questions to be solved. No? For example, we have three of them. The first one, how to determine if a sample is consistent or not. The second one, how to select the reference sample in order to use it for equation of state matching. And a third one, how to proceed if the samples are highly contaminated, for example, or if we have low sample volume. So again, we can apply fast automated workflows to help the engineers in the decision making related to fluid characterization. No? This Neptune fluid data suite, as Daniel have commented before. Let me go. Oh, sorry. Oh, yep. Okay. So sampling is one of the most important activities during the development phase, making possible to recover a reservoir fluid sample that can be analyzed in our laboratory. No? However, the main challenge we have with this analysis of the fluid samples is the fact that we cannot measure the full reservoir composition. The crude samples are composed by a huge number of components that cannot be measured in a chromatographic analysis. So we need to make a set of assumptions playing with a grouping of components called pseudo-components for the composition from C7+. So that's the reason why it's not only enough with measuring fluid composition. We need to analyze also a set of pressure, volume, and temperature experiments called PVT, and also flow assurance experiments to measure gas and liquid and also solid properties to capture the liquid vapor and also the liquid-solid behavior of the fluid. An additional issue we have in those experiments is that these are not standard for all the fluid types. No? We have a big uncertainty present when we measure the samples. No? For example, especially in the near critical fluids or the heavy oil fluids. Just an example, in those cases, the stabilization time of each stage of the PVT analysis plays an important role in the consistency analysis. Because we could have even different results of saturation pressure depending on the way we do the analysis. And finally, with the results of those experiments, as you can see here in the chart, we can match an equation of state in a thermodynamic package in order to capture the behavior of the fluid at any pressure and temperature condition, no? Obtaining a full fluid characterization that can be used as input for our reservoir, production, or facility simulation models in an integrated way. No? Regarding the first step, which is the sampling, we could have different issues here or uncertainty points, let's say, depending on the type of sampling performed. For MDT samples, the most important point is to reduce as much as possible the contamination of the sample, especially if oil-based mud is present and has been used during drilling. This mud is fully mixed with the hydrocarbon fluid, so it cannot be physically removed. So the PVT analysis should be done to contaminated samples, and it increases a lot the uncertainty of the results. In order to reduce the contamination of the MDT sampling, we can apply downhole fluid analysis, no? But however, sometimes the measurements of this is not very accurate, and finally the contamination is higher than we estimated. On the other hand, for DST samples, the most important point is to assure that the sample has taken at stable conditions. Initially in the DST operation, a cleanup period is performed to clean the well, and after this, the downhole pressure is monitored in order to evaluate an appropriate time for sampling. But sometimes no stable period is reached, and samples are taken during oscillations. So this fact increases a lot the uncertainty also, because fluid cannot be taken at monophasic conditions sometimes, in case especially for bottom hole samples. Or, for example, in the case of surface samples, the gas-oil ratio we measure is not representative from the fluid. No? The point we want to highlight here is the importance of the reviewing of the sampling reports and also the PVT reports in detail in order to capture these potential sources of inconsistencies. So after sampling, the fluid samples are analyzed in the PVT lab and also the flow assurance laboratory. And as mentioned previously, these experiments are not 100% standard, and some inconsistencies could be obtained. No? So it's necessary to implement a guide process, fast also, to quickly evaluate the consistency of the analysis, even while the samples are still in the lab. And based on automated criteria that we apply to the different experiments, we can evaluate the sample representativeness. So we need to answer again some questions, no, regarding the QAQC process, no. This automated QAQC process is based on responding the following questions, no. The first one is if the sample was properly taken or not. In this case, we apply the sampling criteria. If the sample has been preserved properly or not, we apply the opening criteria. If the lab results are consistent or not, we have different individual checks to the different lab experiments, such as the composition, the constant mass expansion, the separator test, the differential liberation, the constant volume depletion, etc. And also the last question is to validate if the lab results are consistent, but not only individually, but also among them. No? For example, we compare some properties from flash experiments versus differential liberation, or CBD versus CCE experiments. Now, in the following slides, we are going to show you some examples of these automated checks. Some of them, as you will see, are very simple, but some others require more complex calculations. The first example of automated checking is the sampling criteria, and it's dependent of the type of sampling performed. If it's a bottom hole sample, we need to assure that the sample is monophasic, no, as we commented previously. We can compare the saturation pressure measured in the CCE experiment versus the bottom hole flowing pressure measured during sampling. If the saturation pressure is higher, the sample is not representative. So potential causes could be, for example, non-stable period during the DST bottom hole sampling, as explained before, or a big drawdown in case of the MDT sample when sands are tight, or if reservoir fluids is really close to saturation pressure. On the other hand, if the separator or surface sample is taken, the most important point we need to assure is that the gas-oil ratio measured is correct, no, and representative. We can check it comparing the saturation pressure measured for gas and liquid phases at separator temperature. And if these phases, the gas and liquid, are equilibrium conditions, the saturation pressure should be equal between them, no? And should be equal to separator pressure, sorry. So if that is not the case, some inconsistencies are present in the gas and liquid composition. Potential causes of this uncertainty could be, for example, huge instabilities at the separator that makes difficult the GOR measurement, or if there is a liquid carryover in the gas train, that will alter the gas composition. Or if there is a condensate banking at the near wellbore, the separator could not be representative of the reservoir fluid, and the gas and oil compositions could be altered. A second example we want to show you of automatic checking related with the compositional analysis is the Hoffman plot, no? That most of you probably already know. Here we need to assure that composition partition between the gas and the liquid component is consistent, following a linear trend. We can directly apply a linear regression coefficient calculation to check it. And as you can see in this example, the linear regression coefficient obtained is 0.99. So both both for separator liquid composition and for recombined fluid composition, which means that it's consistent. The information is consistent. So some of the problems that may occur during this experiment that is causing inconsistencies in this checking could be operational problems, for example, compositional or component losses, or again, liquid carryover, no? And also we could have chromatographic analysis issues, such as, for example, a bad baseline in the chromatographic analysis, or issues during peak identification and integration, and can alter our results. This is another example of the check-ins performed to compositional analysis. To show you the importance of the composition, no? Because the composition is the baseline for the question of state matching, and if it's not correct, it will complicate a lot the matching afterwards. So the first check is to assure that the calculated properties of the plus component are consistent with the rest of the composition. We need to check first if the molecular weight of the stock tank oil is calculated or measured. And if it's calculated, some uncertainty in this value should be considered. No? And secondly, how the mass balance is closing, considering the molecular weight and the specific gravity of the plus fraction. Here we show you an example of our automatic tool to check this mass balance. On the other hand, of the right side, we include that it's necessary to assure that proper single carbon number properties are considering to calculate the mole fraction from the mass fraction. No? In case it's possible, we highly recommend it to perform a micro distillation using very low amounts of liquid, just only 25, 50 cubic centimeters, in order to determine experimentally the real molecular weights of the fractions, reducing the uncertainty in the molecular weight and also in the composition, the molar composition. Here we show you a picture of the microdistillation we have in our Repsol Technology Lab, and an example of the results we have with it. No? So apart from the compositional analysis, we also analyze the consistency of another common experiments to oil and gas samples, such as the CCE or constant mass expansion experiment. Here, the objective is to check the relationship between the pressure steps and the relative volume changes through a variable called Y function. This Y function should be linear versus pressure, so a linear regression coefficient again could be automatically calculated, no, as previously in the Hoffman plot. Sometimes Y function results seems to be so perfect, as you can see here, no? But that means that the relative volumes have been calculated to successfully accomplish this criteria are not the real ones. So be careful with this data. No? Many other times we could have some inconsistencies, especially for the pressures close to the saturation point, as you can see in the other plot. Most of them are related with the uncertainty in the volume measurements, as the differential volume could be very small in those stages, and it could be very difficult to measure properly those volumes. So this behavior is shown here, and in those cases, the results are not discarded, but an alert should be considered, no, for these stages. Now we put some examples of the consistency analysis of experiments done specifically for oil samples, such as the differential liberation analysis. No? In this case, we applied a set of different check-ins, but we are showing here just a couple of them. Both of them are mass balanced. The first one aims to assure that the volumes measured, taking into account the liberated gas per stage, are consistent with the rest of the properties. We calculate the formation volume factor and also the liquid density for each stage based on the rest of available data. We start at ambient pressure and back calculate these properties at higher pressures. Then we compare the calculated values with the reported values per stage, and we calculate an average error. For example, in the sample we show here, the average error is low, no? So we can accept those results. But sometimes there is a high error, especially in the lowest pressure stages, because of the volume uncertainty that is transferred to other stages. The second one of the right side is a more detailed material balance per stage, but at component level. in order to assure that partition coefficients follows a monotonic trend and there is no crossing between components. So the heaviest components have the lowest partition coefficients. So here is an example where all the trends are correct and we can consider this data as consistent. No? That's why the traffic light is green. But again, the measured volumes or the liberated gas composition uncertainty could lead to inconsistencies here in both criteria. On the other hand, here specifically for gas samples, we show you an example of the consistency analysis of the constant volume depletion experiment. As in the differential liberation for oil samples, we applied a set of different check-ins, but we are showing here again just a couple of them, being again the material balance. The first one is based on comparing the calculated liquid density with the reported liquid density. So no major differences should be obtained. So the calculated liquid density value should be lower than 1 grams per cubic centimeter, which is the density of the water. Here you can see, for example, a case where the calculated liquid density is reaching a value up to 4 grams per cubic centimeter, no? In many stages, which is not physically realistic. That means that there is a volume uncertainty affecting the density calculations. And additionally, on the right side, we apply the same material balance again as in the differential liberation to calculate the partition coefficients per component. But in this example, differently than in the previous one, we can see a different behavior, no? Than in previous case. Here we observe that a lot of components are crossing between them, and there is no monotonic trend we have in all the components. So we will discard those results, assuming some uncertainty in the constant volume depletion results. And now, after showing you some examples of the individual consistency check of the PVT experiments, the following steps should be to evaluate the consistency of the experiments, but among them, no? As explained initially. We are going to show you two different samples, one for oil samples and another for gas samples. The first one that is showed here is to compare the API and GOR obtained in the flash experiment versus the ones obtained in the differential liberation experiment. The more stages the separation, the light ends should concentrate in the gas phase. No? So API should decrease as more stages are used to separating the vapor from the liquid, and the GOR should increase instead. Here we can see an example where the consistency is assured because the API of the flash experiment is higher and the GOR is lower. But sometimes flash experiment presents some inconsistencies because the equilibrium has not been reached properly during this depressurization. And another example of the consistency between the different experiments is the comparison of the liquid dropout obtained in the CC experiment versus the one obtained in the CVD experiment. For the first stage of the saturation, the values should be equal as there is no material release from the cell. But from the second stage, the CVD liquid dropout could be higher, and finally the trend shifts. So here we have two examples, one where the results are consistent, another where it's not. Most of the times the inconsistency are caused by the uncertainty, again in the volumes measured, when the liquid dropout values are especially below 1–2% more or less. Additionally, the equilibrium time here is key. No? As I mentioned before, for some kind of fluids, it's necessary to increase significantly the stabilization time per pressure stage in order to obtain consistent volume measurements. Additionally, apart from the consistency analysis of the PVT experiments that we have explained previously, it's necessary to perform also a QAQC task to the flow assurance experimental data, which is also linked with the sample representativeness. Here we have included two samples, how the wax appearance temperature and how the asphalting content correlates versus API density. No? In the wax appearance temperature plot, as you can see, there is no trend here. There is a huge uncertainty in the wax appearance temperature measurements. However, in the case of the asphalting content, it's a clear trend with API, so we can validate those analyses. So, summarizing the benefits of the workflow, the automated QAQC analysis first can help us to define if a sample is consistent or not, if we totally discard it, or if we consider 100% valid, or if we consider it valid, but assuming some uncertainty in some properties. Based on these QAQC results and its comparison versus the different samples taken from the sampling campaign, we can select what is the reference sample to be used for equation of state matching. Usually that will be the one with more consistent data, with more green traffic lights, let's say. But what about if there is no enough representative data to perform a proper fluid characterization? Well, in this case, we use the same predicted algorithms explained in the first section by Daniel that were targeted for exploratory phase, but we can use it also in these stages, no? During development and also even in production phase. So we can apply the workflow to allow us to predict depending or inconsistent properties from the validated ones. And finally, the last check-in, but not less important, that should be considered is in a completed QAQC process, is to evaluate the fluid data, but in an integrated way, no? Comparing the properties between the different sampling points of the reservoir, if they are available. We know that the reservoir composition can vary laterally between faults, but also vertically, no, because of the depth. So we can carry out a visualization of the main properties to evaluate the potential fluid trends. If in case there is an outlier, we need to consider some inconsistency in that sample. So we have included here two examples of, or three, in fact, samples of saturation pressure versus depth. If all the samples are coming from the reservoir, a linear trend versus depth should be obtained. No? So as you can see in two of the plots, there are samples not following the trend. So we need to be careful with that and analyze why they are not following the trend, if there is some inconsistency or there is no connectivity between those reservoirs. So the main takeaways of the key takeaways of the development phase are summarized here. No? First one, it's recommended to perform the QAQC analysis as early as possible, even with the sample is still in the lab, to detect inconsistencies and have been able to repeat the experiments if possible. Do not leave aside the composition in the QAQC, not at all. It's the most important piece of the cake. Perform the QAQC analysis in the most integrated way as possible, comparing the results between different experiments and including also flow assurance data in that evaluation and comparison. And finally, a unified or common fluid model should be used through all the production system, no? From reservoir to facilities, assuring the fluid consistency between all the different sites of the network. So finally, the main summary message we want to emphasize in this presentation is that from very early stages, it's required to take decision based on fluid characterization. Fluid characterization is one of the pillars of the field development. So it's key to use integrated workflows to store, visualize, generate, validate, or even forecast the fluid properties along the field life cycle. In the very beginning, the uncertainty is huge until you have a fluid sample. So we need to assure having a proper workflow to estimate the fluid properties from analogs or correlations, and also uncertainty limits based on Monte Carlo simulations, for example. And when a fluid sample is taken, it's still necessary to play with uncertainty, no? And the QAQC of the laboratory data is also key to assure the representativeness of the fluid properties, and not only individually, but also in an integrated way, evaluating the fluid trends if possible. So thanks a lot for your attention, and now it's time for the questions. I'm going to stop sharing.
Yeah, perfect. Thank you so much, Veronica and Danny. Really, really good and comprehensive work. Very, very fascinating. We've gotten some questions in the Q&A box and also in the chat box here. Just due to time, since we only have 5 minutes, I'll try to keep it to that. But we'll start with some low bowler questions. The first one is for you, Danny. In your experience, is it always possible to derive an integrated EOS or a unified EOS, i.e. one that describes the fluid under both reservoir conditions and surface conditions?
I would say yes. And many times when you are facing big challenges to unify different fluids, is because of either problems in the lab for the behavior or problems in the lab with the composition. The truth is that we encounter the most challenges when we're mixing things from different laboratories, no? Because you have to be careful that they're using the same molecular weight tables, that they're actually quantifying the molecular weight in the same way. So sometimes we have to tweak those parameters in order to satisfy the comprehensive view. So I would say yes, unified equation of state should be the goal in every single reservoir, and but also they're asking about subsurface versus surface. No? And again, I believe that separator test plus let's say experiments closer to the reservoir, you can tune them together, no problem. I understand that also the issue could be the number of components that you put into that equation. No? So typically what we do, we generate one, let's say, full range equation of a state, and later on maybe the reservoir team wants to work with a reduced number of components. Maybe that implies extra tweaking, but we still have that reference unified view for everybody. And also the production engineers may want to work with black oil tables. Instead of generating them independently, we try to work that table from the equation of a state. So I'm optimistic, and I do think that it's feasible.
Okay. And I think in general, that's the same finding as what we found in our studies. So that's great to hear that there's some consistency there. Over to a little bit on that same question, Danny, when it comes to creating this unified equation state, do you allow for also compositional adjustments and try to, like, you mentioned the molecular weight tables, etc. And can you put some flavor onto what kind of changes you're potentially doing there?
Just to emphasize what Veronica was explaining on sensitivities, trying to close the mass balance, maybe with a plus minus 5% of the molecular weight, that will give you a different mole percentage. No? So I would say that's one of the key things that we try to do. But also the GOR. Remember that in the end you're calculating the gas and the liquid separately. No? And what we try to emphasize is not to just take blindly the composition in mole percent coming from the lab, right? And allow yourself to either through the molecular weight or the ratio gas to liquid in the GOR, start seeing what makes more sense. And maybe for a single sample, single reservoir, you don't need this. No? You can always tweak whatever other property. But when you're trying to unify many fluids, that's key, because that's, let's say, a degree of freedom that you use in one fluid in a way differently from the others. If you're trying to do a unified equation of a state, critical pressure will affect all of your fluids. No? So if you touch it, it will be for all the fluids. So it's actually the composition, the only element that you can play fluid by fluid. And that's where, as Veronica was explaining, knowledge of how much uncertainty you actually have in the lab, what are these ranges of variability, gives you that opportunity to play, always keeping some limits. Of course, I mentioned 5% before. That's where what we try to stick to.
Excellent. And then for Veronica, there's a question a little bit along the lines of what you're talking about now, Danny. If you can, is it really possible to use one unified equation of state model for the entire network and taking into account all the compositional changes that you're observing during the life of an active field?
Yeah, it's possible. Sometimes it's not easy, but as Daniel has mentioned before, it's possible. No, our idea is to try to use an integrated fluid as much as possible in order to assure this consistency between the different parts of the network. No, for example, if you can use a compositional approach in the reservoir modeling, that will be perfect. No, sometimes it's not possible because it takes longer because the simulation times are quite huge. But in case it's possible, especially for gas condensate or this type of fluids where we could have a lot of variation in composition versus field life, we recommend to use it to capture this variation in compositions versus time, and transfer this variation into production systems and facilities also in an integrated way.
Very good, very good. So I'm afraid we can't answer all the questions, but the last question I'll ask to you, Veronica, and it's whether or not the slides will be distributed.
The slides will be, sorry?
Yeah, or they will be available for the audience. That's a few questions from the audience, if they can get the slides in some way.
Yes, I think that would be possible. Yeah. Yes, yeah. For sure.
Excellent. Okay, thanks a lot again, and thanks for all the participants. The recording will be distributed to everyone, and also we'll try to get the slides there as well. And if you have any follow-up questions, feel free to reach out to Veronica and Danny directly. And then yet again, thank you again to Veronica and Danny, and have a good rest of the day.
Same to you. Thank you.